How's exam 1? I don't often succeed in producing laughter by an exam. But scores will be up this afternoon. 12 points a question. So you can see at a 200-point base, given that 12 times 24 is a hell of a lot more than 200, as I have told you with the information on the syllabus. For each exam and quiz I give, there's a whole bunch of earnable extra credit built in. Because this stuff is tough. And I want to show you what chemistry is about. Upshot, I provide you with the opportunity to not be tortured by exams which contain questions, all of which you cannot deal with successfully at the time at which you take the exam. But I will tell you right now, when we get to exam 2, I will by that time have surveyed exam 1's results. I will see which questions and problems have fallen into the most commonly missed category. I will identify these questions and problems with the solution key that I post. Because on exam 2 we will revisit these questions to give you the chance to show me at the time of exam 2 that, yeah, I got this stuff now. That's what we want. We want you to learn it. So we proceed with additional special topics considerations regarding quantitative analysis of solutions of Bronsted-Lowry acids and bases. We shall, in short order fashion, as I reminded you earlier, introduce ourselves to the remaining consideration we have to make in order to analyze any water solution containing any Bronsted-Lowry acid-base species. To the extent that we'll be able to evaluate quantitatively the composition of the system, find out how many moles of everything that's in there are. Powerful tool. That consideration is charge balance. We'll be there shortly. Now, first, a couple more fundamental aspects of Bronsted-Lowry acid-base equilibrium analyses. In particular, how do we get at solution pH if we're dealing with a solution that's particularly dilute? Like 3 times 10 to minus 8 molar HCl, which is the solution of this nature which is discussed in the notes. Well, first of all, don't fall into the trap of taking the hydronium ion concentration for this solution to be 3 times 10 to minus 8 molar. There's no question the HCl ionizes 100%, and it makes that contribution to the solution hydronium ion concentration. But if you take 3 times 10 to minus 8 molar as the hydronium ion concentration, you will report this solution to have a pH greater than 7. How the hell can an acidic solution be basic? So here is the first look at an example of a solution where, in order to get the hydronium ion concentration determined correctly, we have to consider the contribution made to such by the autoionization of water, by the Kw equilibrium expression. So I've done that for 5 times 10 to minus 8 molar sodium hydroxide solution. Where here, if you tried to determine solution pH strictly on the hydroxide ion contribution made to the solution by the solute, you'd report this basic solution to be acidic. This is impossible. That's why I have reminded you. What counts first, foremost, always is chemistry. Then we'll do business with arithmetic as necessary. So here is the Kw equilibrium reaction. And in this system we know the sole source of hydronium ion is this reaction. Water reacting with water is the only way we get hydronium ion in this system. But in this system, because of the solute, we have two sources of hydroxide ion. The amount given to the system by this reaction plus the amount given to the system by the solute. So hydroxide ion for the solution is the sum of these amounts. X represents the contribution to the hydroxide ion molarity by water reacting with water, and 5 times 10 to minus 8 moles per liter from solute NaOH. Now we've done the chemistry, the rest is not difficult. We write the Kw relationship, which now is algebraically is expressed here, and we ask the question, how do we solve it? If you multiply it out, it's a quadratic. But you know I'm not solving this with any quadratic recipe. I prefer instead to solve it by thinking about the chemistry of the system. Because that's what I'm trying to do in this gathering. Learn chemistry. So I start by saying, given that this solution is very dilute, you accept that statement? X, which corresponds for this system to the hydronium ion concentration, has got to be, value-wise, close to what number? What is it? 1 times 10 to the minus 7. Yeah. That's a reverse YOP. YOP! 1 times 10 to the minus 7. This solution is damn near like pure water, but not quite. So now, I know what kind of values for X to focus on to solve this thing. Since the solution is basic, I will expect X to be a little bit bigger or a little bit smaller than this. A little bit smaller. Pick me an X value that's close to, but a little bit smaller than 1 times 10 to the minus 7. I'm listening.
8 times 10 to the minus 6.
8 times 10 to the minus 8. Let's put in 8 times 10 to the minus 8. This is not difficult arithmetic. Five plus 8. 13. Yes?
In this case, X represents the amount of hydroxide ions that are from the water, right?
As well as the hydronium ion concentration.
Yes, but like X is, like you have the concentration of hydronium ions that come from the solute, but X is more than water, right?
Huh? Hydronium ion is not coming from solute. It's coming from this reaction. This is in water solution. You remember that? Now then, here comes the hard part, arithmetically speaking. What's 8 times 13? 8 times 13. 104. So this becomes 1.04 times 10 to the minus 14 when I make decimal point adjustment. Is that pretty close to 1.0 times 10 to the minus 14? You're damn right it is, and that's the answer. Now, if you would have tried 5 times 10 to the minus 8 or 9 times 10 to the minus 8, you would have got a value for this product that's close to Kw. But no value for X gives you a value that's closer to Kw than 8 times 10 to the minus 8. It's not difficult. I mean, if, for example, you tried first 5 times 10 to minus 8. Let's try it. 5 times 10 to minus 8, okay? That makes this 1 times 10 to minus 7 times 5 times 10 to minus 8. That gives you 5 times 1 is 5 times 10 to minus 15. Too small. So I haven't done anything fancy. And with the first try of 5 times 10 to minus 8, I already realized whatever the hydronium ion concentration is, it's bigger than 5 times 10 to minus 8. And I'm limited to one significant figure by this solute concentration. So if I know that the hydronium ion concentration is bigger than 5 times 10 to minus 8, and I can express it only to one significant figure, for this solution, the only possible remaining values for the hydronium ion concentration become 6 times 10 to minus 8, 7 times 10 to minus 8, 8 times 10 to minus 8, 9 times 10 to minus 8, or 1 times 10 to minus 7. That's it. So you got this thing boxed up real fast, haven't you? And with the assistance of your push-button calculator, if you need such, testing this is easy. Hell, you don't need a push-button calculator for this. Now, just for curiosity's sake, how many of you have looked at bonus quiz number 1? Now that exam 1 is over, you can concentrate on bonus quiz number 1. You see the question on bonus quiz number 1, which asks you to calculate the concentration, the M sub I value, the label on the bottle, for an acetic acid solution in which solute acetic acid is ionized 100%. The two significant figures. I do this to get you to recognize the need to pay attention to significant figures. Now let's talk about another issue which relates specifically to that problem.
Oh yeah, is it actually possible for the acetic acid to literally ionize 100%?
The two sig figs, you're damn right, and you're going to figure out that concentration value if you do the problem correctly. Here we go. This stuff is hard enough without me giving you a problem that can be solved.
I'm still trying to understand. Can you explain again instead of 5 times 10 to the negative 8 plus F?
I think you're looking at an algebra puzzle. You see me one-on-one after class and I'll get you untangled on this. Now then, max percent ionization as a function of dilution. We have recognized any acid or base whose ability to ionize is subject to equilibrium control, which means a weak acid or weak base. An acid for which we, if it's in our table, we see a Ka value tabulated. A base for which, if it's in our table, we can calculate Kb because the corresponding Ka value for its conjugate acid is in the table. Any such acid or base reacts with water to an ever-increasing extent as we enrich the ratio of water to the acid or base, as we dilute. How far can we get this acid or base to react by dilution? That's what this is about. Now the analysis, the rigorous quantitative analysis of this system is on page 1839, so I'm not rewriting that. You can read that, but I'm going to talk to you now about the nitty-gritty of this analysis. Number 1. If for an acid solute, same would apply to a base solute. If the Ka value for the acid solute is bigger than 1.0 times 10 to minus 7, then by progressive dilution, we can get this acid to ionize to an extent which exceeds 50%. Notice the impact that this has if you are going to, for a very dilute solution of such an acid, write PSI. Because now you might in fact be writing hydronium ion and the conjugate base. Because if this stuff is reacted to an extent which exceeds 50%, the hydronium ion molarity and the conjugate base molarity will each be larger than the solute acid itself, which is contrary to the way we generally inventory, PSI, solutions of a weak acid. Because at fairly substantial concentrations, like 100th molar or greater, it's always going to be the acid. That's the principal species. When you start making a solution real dilute, then you change the chemistry of the system. It really relates to this, what we just did here. Because factored into this puzzle is the autoionization of water. Because when we have a water solution that's diluted to the maximum extent, how do they express this in math class? An infinite extent. Isn't that maximum? If we have a solute acid or solute base diluted to an infinite extent, and water's the solvent, what is the hydronium ion concentration for the solution? I'm listening.
Isn't it just the same as water? 1 times 10 to the negative 7?
Absolutely, it has to be. You've diluted this solution to such an extent that practically speaking, you're dealing with pure water. How about that? I assure you, if you take the average size swimming pool at an apartment complex, or we can go over here to the Gator swimming pools where the Gator swim team practices, fill that up with deionized water and throw in 1 molecule of acetic acid. Is that acetic acid molecule going to ionize? Yes or no? Yes. You're damn right it is. Which means it ionized 100%. There's only 1 molecule. How about that? Now, do you think by measurement you're going to be able to find out that the pH of this acetic acid treated swimming pool is greater than 7.0? Hell no. That's what this analysis rests on. So what the analysis shows you, and again I'm not rewriting it on the board because you got it in the notes, you're looking at it. Is that an infinite dilution? We know the hydronium ion concentration for the solution. We know the hydroxide ion concentration for the solution if it's a solute base. And we know how percent ionization is defined, don't we? So by application of that definition, we wind up with deriving a recipe for maximum extent or percent ionization for the acid or base based on its Ka value. You'll read through the recipe if you're interested in the derivation. I have no intention of holding you responsible for this derivation. I've given it to you. But on occasion it will be necessary to use the upshot, the recipe which follows after the derivation. You see the recipe? The recipe reads Ka times 100% over Ka plus 1 times 10 to the minus 7. Where the 1 times 10 to the minus 7 is following from this. That recipe, if you've not noticed such, is on the information sheet that I extend to you for use during quizzes and exams. You have to memorize it, but be able to use it. In order to be able to use it properly, you need to understand it, and the understanding is on this page. Numerical considerations apply to this? If Ka for the acid is bigger than 1.0 times 10 to the minus 7, this solute Bl acid can ionize by dilution to an extent which exceeds 50%. If Ka is big enough, you can get it to go to 100% with significant figure limitation, like the acetic acid solution that I've asked you about on the bonus quiz. And 1.8 times 10 to the minus 5, which is Ka for acetic acid, is 180 times bigger than this number. But if Ka or Kb is smaller than this number, I don't care how much you dilute it, you can't get to 50%. Why not?
Because water's a stronger acid.
Don't forget, let's write this equilibrium reaction. By definition, this equilibrium reaction is Kb for acetate ion. Okay so far? And Kb acetate ion is 5.6 times 10 to the minus 10. Which we can calculate from Ka acetic acid, which is 1.8 times 10 to the minus 5. Do you see what would happen if we imagined treating a water solution of acetate ion with additional water? We're diluting, trying to get this thing to go left to right 50%. Tell me, between which pair of species, this and this, or this and this, do we have the greater tendency for H plus exchange to occur? Between these two, or between these two? Isn't this a good deal stronger acid than this? Isn't this a good deal stronger base than this? And if you have considered the possibility of getting this to go 50%, you've now created a system in which the molarity of this is equal to the molarity of this. So now you have an H plus giver, which has a strength that far exceeds the ability of this to be an H plus taker. That's why you can't get it to go to 50%. So we could add to this statement, if K is smaller than 1 times 10 to the minus 7, you can't get it to 50%. I don't care how much you dilute it. And the smaller is Ka, the smaller is the max extent ionization. Ka ammonium ion, which numerically is the same as Kb acetate ion, 5.6 times 10 to the minus 10. Take a look at that recipe. Ka over Ka plus 1 times 10 to the minus 7. Ka ammonium ion, 5.6 times 10 to the minus 10. Divided by 5.6 times 10 to the minus 10 plus 1 times 10 to the minus 7. What is the result of adding 1 times 10 to the minus 7, 1.0 times 10 to the minus 7 to 5.6 times 10 to the minus 10? What is the result of that addition?
1 times 10 to the minus 7.
It's 1.0 times 10 to the minus 7. And 5.6 times 10 to the minus 10 divided by 1.0 times 10 to the minus 7 times 100% is what? What is it? 5.6 times 10 to the minus 10 divided by 1.0 times 10 to the minus 7 times 100%. What do I get? How much percent?
0.5.
0.56%. That's it. You cannot get an ammonium ion to react by dilution to an extent which even gets to 1%. It's too damn weak in acid. That's why, for example, if you make an ammonium ion buffer, and the ammonium ion molarity is 1,000 times bigger than the ammonia molarity. The ammonium ion molarity is 1,000 times bigger than the ammonia molarity. System's still basic. Because ammonium iron's ability to give H plus is pretty damn feeble compared to the ability of its conjugate base to swipe H plus. We're talking more and more about what these Ka and Kb values mean chemically. That's what counts. All right. Question 1846 says, calc max ionization extent for, I don't know, HOCl. That's plug and chug. Just use the recipe, 22%. Question 1847. Question 1847 is arguably somewhat of a trick question, a dirty pool question. A dirty pool question, as I see it, is a question that's about chemistry. That's surprising, isn't it? It's about chemistry. That you may not have thought of yet. So now I'm going to provoke you to think about it. Question 1847 says, if I got a weak acid, like ammonium ion, with Ka 5.6 times 10 to minus 10, which we just told you, by dilution, cannot be made to ionize to an extent which exceeds 0.56%, less than 1%. But is it possible to get ammonium ion in water solution to lose H plus for all the ammonium ions present to an extent which exceeds 50%? Is it possible to get ammonium ions in water solution to, practically speaking, lose all their H pluses? You're damn right it is. How's it possible? Not by dilution it's not possible. How's it possible? And a stronger base, you betcha. You put ammonium ion in with hydroxide ion, all of a sudden ammonium ion is behaving like a strong acid. How about that? That's why we told you earlier on, these Ka values, Kb, they depend on this material with which the stuff is reacting. So once you talk about a Ka for an acid, you have to specify what is the base that these Ka values are referenced to. And in water solution, that's the solvent. In any solution, it's always the solvent. That's why we asked you earlier on, if you were to evaluate Ka values for acids in ammonia solvent, hey, all these Ka values we're looking at in our table would be a hell of a lot bigger, because ammonia is a hell of a lot better proton grabber than water. That makes acids behave much more strongly. That's the chemistry of it. That's where the understanding lies. Then you can do the arithmetic. All right? Now more fun. Polyprotic acids. If you've read the information in the notes, you know that there are 3 subcategories of polyprotic acids. We could apply this analysis to polyprotic bases. What's a polyprotic acid? An acid which has the capability, on reaction with water, to give more than 1 mole of protons per mole of acid, the most common of which is sulfuric acid molecule. Because under appropriate conditions, a molecule of sulfuric acid will react so as to give more than 1 mole of H plus. Under specific appropriate conditions, we can get a mole of sulfuric acid to give away 2 moles of H plus. That makes it diprotic. How about the condensed formula for phosphoric acid, H3PO4? Would you accept my definition of H3PO4 as a triprotic acid?
Yes.
Because per H3PO4 molecule, under appropriate conditions, you can get that thing to lose 1, 2, 3 H pluses. Triprotic. Well, by definition then, that makes phosphate ion. PO4 3 minus, which is not the conjugate base of phosphoric acid. nor is phosphate ion the conjugate base of dihydrogen phosphate ion, but it is the conjugate base of hydrogen phosphate ion. Condensed formula HPO4 2 minus. Because when HPO4 2 minus loses one H plus, you got the phosphate ion. So in terms of poly, what kind of base is phosphate ion? It's a triprotic base. You can collect one H plus and become HPO4 2 minus, two H pluses become H2PO4 minus, or three H pluses and go all the way back to the parent phosphoric acid molecule. So that's language. Now then, three types of polyprotic acids. Number one, the parent acid is molecular and strong. The only obvious example of such that I know of is the sulfuric acid molecule. But sulfuric acid and sulfuric acid solutions are very commonly dealt with, so we'll pay attention to this particular polyprotic acid, specifically diprotic. Molecular, strong. Next subcategory, which we'll analyze next, is a polyprotic Bronsted acid, which is also molecular, but the parent acid is weak, like phosphoric acid, like H2S, like quote-unquote H2CO3. These are all weak, polyprotic, molecular Bronsted acids whose formulas appear in our acid-base table. And then comes number three, the real fun one, the hydrated metal ion acid, which are all polyprotic. Like, for example, this stuff, hydrated aluminum ion. You see this formula in our acid-base table in the acid column. Any of you in 46 laboratory as yet in assignment 4? If you are, you're really zooming along. But when you get to assignment 4, you'll find out that the way we test for the presence of this ion in water solution, beside pH measurement, because this in water solution at a molarity of 1 shows a pH of about 2.8. Ka for this is just a little bit smaller than Ka for acetic acid. Maybe it's 2.6. 10th molar of this shows a pH of 3. Fairly acidic solution. But the way, beside measurement of pH, we test for the presence of this in solution is to give this the opportunity to react with a base like hydroxide ion or ammonia or carbonate ion. Different bases will do it. But those are three bases that you deal with in the laboratory. So I mentioned those three. To form a precipitate. There's the formula for the precipitate. Call it hydrated aluminum hydroxide. It's not a very nice material because it's an amorphous gel. It's a gooey stuff. It cannot be prepared pure because as you form gooey stuffs, they trap stuff that was in the solution as they were formed inside themselves. Like a goo, a jelly. But regarding the polyprotic nature of this acid, how many H pluses do you have to pull from this to make this? 3! Nothing fancy about that. So this is triprotic. But the upshot of this is to realize, to calculate the hydronium ion concentration for a water solution of a hydrated metal ion acid, now you've got to do some pretty fancy stuff. That's why we put the analysis of this particular type of polyprotic acid last. And it is that time when we will introduce you to charge balance, because that consideration is required to do this calculation. So we'll take this off the slate and return to it shortly. The arithmetic regarding that analysis, as we've just mentioned, is most challenging. So we go to the sulfuric acid solution. First, I've written here the reactions that you must consider to calculate the hydronium ion concentration for any water solution of sulfuric acid. Second, unless the sulfuric acid solution is so damn concentrated, like you got to take it up to about 12 molar, all the sulfuric acid molecules dissolved will ionize. You recall that sulfuric acid is categorized as a strong acid by the way it's listed in our acid-base table. In fact, if you go back and look at the acid-base table, you see that in our acid-base table, in terms of pecking order, in terms of strength, sulfuric acid occupies the number 2 position. We only got 5 strong acids listed in our acid-base table. Perchloric acid, strongest, sulfuric acid, hydrochloric acid, nitric acid, and then hydronium ion. That's it. Only 5 strong acids in our table. Therefore, since we're not going to consider any such exceptionally concentrated sulfuric acid solutions, reaction 1 is a reaction which always goes to what extent? 100%. Now what's that mean in terms of getting hydronium ion concentration?
It's the same molar concentration as whenever sulfuric acid was.
Say that again.
It means that the concentration of hydronium ions is the same as the concentration of sulfuric acid.
Not the same as, but at least that. That's right. So now when you're looking at the label on the bottle for sulfuric acid solution, the M/I number, you know that in that solution of sulfuric acid is a solute, the hydronium ion concentration has got to be at least as big as that M/I number, because this thing went 100%. Okay? Now then, how does the hydronium ion concentration for the sulfuric acid solution likely become greater than M/I? Because of this second reaction. Where hydrogen sulfate ion, the conjugate base of the sulfuric acid molecule, is an interesting base because in water solution, this base can't behave as a base. Look at the acid-base table. You see the hydrogen sulfate ion is, of course, listed in the base column because it's the conjugate base of the sulfuric acid molecule. But do you also see that it's a weaker base than water? So this base, it's minus. It's a minus thing. Anything which is minus has got to be a base. Anything with one or more non-bonding electron pairs in its valence environment has got to be a base. These are all species capable of grabbing H+. Does that mean they will grab H+? Hell no. You cannot escape from the realization of understanding the chemistry for the species. But then we look at the acid column, and you see this HSO4 minus, HOSO3 minus formula there too. And you see in the acid column that this is the strongest weak acid we have in the table. Does that sound like double talk? Strongest weak acid in our table. Because in our table, hydrogen sulfate ion... Wait, I redid the table. Is it in the table just underneath? Still there?
One other, but...
No, mistake. It's under oxalic acid now. It's no longer the strongest weak acid in our table. It's the second strongest weak acid in our table. So we know that hydrogen sulfate ion has the capacity on a measurable basis to react with water and make hydronium ion. And that's not surprising, given that the Ka value for hydrogen sulfate ion, that's in the table, 1.2 times 10 to minus 2. Does this sound like an acid which, without a whole lot of dilution, can react 100%? You're damn right. You don't have to make sulfuric acid solution particularly dilute to get this reaction also go to an extent of 100%. So, what's the upshot of this? The upshot of having to pay attention to the second reaction. Here's the upshot. We said that in any sulfuric acid solution, because this reaction goes 100%, the hydronium ion concentration is at least what? But it's likely this second reaction is going to go to a measurable extent, which makes the hydronium ion concentration get bigger than M sub I. By how much? Don't call it X. I want it spoken of chemistry-wise. Do you see this second reaction? Does this second reaction not tell you stoichiometrically that by the second reaction, for every hydronium ion you make, by the second reaction, you also make sulfate ion, don't you? All right? Consequently, the hydronium ion concentration given to the solution by the second reaction is equal to the sulfate ion molarity. So there you have it. There's the hydronium ion concentration for any water solution of sulfuric acid. The label on the bottle plus the sulfate ion molarity. Now then, in terms of chemical components of this system, what's M sub I equal to? This is the chemistry. With understanding this, you can do business with any sulfuric acid solution. And if you don't understand this, you're going to be lost. First reaction goes 100%. So after the first reaction, the value for the concentration of this is M sub I. And the value for the concentration of this is M sub I after the first reaction. Okay? Now goes the second reaction. So the concentration of this, expressed initially as M sub I, gets smaller, doesn't it? Gets smaller by how much? By this much concentration, doesn't it? This tells you that M sub I is equal to this. I'll use the condensed formula for hydrogen sulfate ion. Done. With these two statements, you can now deal with any sulfuric acid solution. And if you don't understand these two statements, then you're lost. But they follow from the chemistry of the system. And if you want an analysis, which may be at this time a little bit easier to digest, we'll play a game. There's the label on the bottle. 100. Okay? The first reaction now goes. After the first reaction goes, how many of these do we have? And how many of these do we have? And how many of these do we have remaining? Now the second reaction starts. How many of these do we start with? Now, let's pick an extent. You pick. What do you want? 25%. We're going to pick the second reaction going 25%. Now watch out, this is really tough. 25% of 100. What is this? 25% of 100 is how much? Good! 2 goes 25%. I told you, I got to get these high school math teachers out and horsewhip them or something. I mean, that's all right, we're getting there. So if this goes 25%, after the second reaction goes, what number do I apply to this? And what number do I now apply to this? Because 25 of it went away, so 75 of it's left. And what does this result as? How much? 100 plus 25. Okay? You see this? M sub I is this plus this. It's 75 plus 25. Not fancy. But this comes from understanding the chemistry of sulfuric acid solution. So we'll pick it up at this point next time. And I'm telling you, you should read carefully the analysis of the ferric nitrate solution, so you can appreciate what we're going to get into next time with determining hydronium ion concentrations for water solutions of hydrated metal ions. That's tough.